Thank you very much. Thank you all very much for coming. So my name is Matija Bucic. I'm interested in probabilistic and extremal combinatorics, but also very much in finding applications of combinatorics to other fields. So at any point in your own work, you run into something vaguely combinatorial sounding, very happy to hear about. So anyway, today I want to tell you something about expanders or expander graphs in whole. So this is one of the perhaps most widely useful class of graphs that people looked at, and they actually have quite a few practical applications such as network design, chip design, but they are also very often useful in theoretical work and absolutely invaluable in combinatorics and theoretical computer science. So there is an amazing survey by Hurey, Lineal, and Vigderson on over 100 pages detailing various applications and cool properties of these kind of graphs. I very much recommend it. Avi is not here, but you can also ask him in general. He is an expert. Anyway, so let me tell you a definition, and I'll draw a picture explaining a bit what I mean by an expander. So graph G is a lambda expander if for every subset U of the vertices of our graph, which is not empty. So these are some kind of very silly conditions just to avoid some kind of contradiction, easy contradictions. So it should not be too big and it should not be empty. Then what you want from it, you want that its neighborhood, so you want that its neighborhood is bigger by a factor of lambda than the size of the set itself. And the neighborhood here is set of all vertices with a neighbor in the set U that we're looking at. So let's look at the picture. I think it's far more illuminating than the definition. So here's our graph G. We want to say that it's an expander. So what do we want from it? We want that if you look at any part, any set of vertices in your graph, if you make one step out of it, so you just look what you can reach by doing one step going out, then this is bigger by a factor of lambda than the size of the set you started. Okay, so in this sense, you are expanding by doing one step. This is why they're called expanders.
Lambda should be below 1 or above 1?
So usually, so that's kind of the point of the talk, but usually you work with lambda being at least a constant and preferably even bigger, because that gives you a lot of cool properties. So everything that I mentioned kind of you get with lambda being, you need lambda to be big for many, many of the properties of expanders. But somehow the point of sublinear expanders is that you can take lambda to be smaller and this still gives you some information and useful stuff. I'll get to that in a moment. But for now,
when you say neighborhood, does not include U itself.
Yes, so I'm talking about external neighborhood. So when lambda is bigger than 1, it doesn't actually matter. When you go into sublinear words, how it starts to matter. Thank you very much. Yeah. So not in U would not U itself. Very good. So these are expanders. So a priori, it's completely unclear why this kind of expansion condition is useful for anything. So let me tell you a nice short proposition, which will at least explain on some level one of the actual practical applications of this. So any two vertices in, say, a 2 expander are a distance suppose 2 log base 2 of n. N is the number of vertices of the graph. So again, a picture, yeah.
You had an upper bound in the size of U lambda over 2. If it's a 2 expander, that means that U can be the whole of the graph.
Yes, I think what I wanted to say here is thank you. Yes. It's really kind of used, yeah, what you want to prevent is taking U the whole graph. Because if you want the whole graph to expand, you just don't have anything else where you can go. So this is why this exists. It's really kind of a detail which never actually comes into play when you do it, but you're perfectly correct. Thank you. I think now I said it correctly. Yes, that should be the correct version. So anyway, so this proposition tells you, again, a picture maybe tells you a bit more than words. So if you take your expander and you take any two vertices inside of it, there is a short path which joins them. So this is also called, the graph has a small diameter, at most 2 log 2n. And not only that, but if you assume a little bit stronger expansion than this, then you actually get this with certain resilience, robustness properties. So not only will you be well connected, but you'll be well connected even if you delete some edges from this graph. And by now you already can maybe see why this is useful in designing networks. Because if you want a network in which you can quickly reach from anyone to anyone, and it's also resilient to outages if storms or whatever breaks your cables, then you can still do it. And so people actually use expanders to design and build networks based on this kind of ideas. The key thing that I didn't mention so far is that you can actually build them with very few edges. So you can find very sparse expanders which still have all of these properties. So the network is also cheap to build. You don't need many cables. So anyway, that's a kind of just picture to have in mind, one application and one exact proposition. So what I have in mind for today is to tell you about the direction which was of more theoretical nature and useful in theory, and to prove some kind of nice results. So the idea dates back to Komlos and Semeredi about 25 years ago. So the general approach, how you might want to use this kind of expanders, is you start with an arbitrary graph and you want to find some structure inside. That's a general type of problems that we look at. You can also work with other structures, but I'll focus on graphs today. So a natural thing to try to do is maybe you can find an expander in your graph. If you can do that, then maybe all of these amazing properties that I didn't tell you about, can use them to find your structure in the expander. So expanders are super nice graphs. They're very useful. We understand them very well. Well, to some extent very well. We can use them to build things, to find objects inside our graph. So the problem with that is that it's not easy or even possible in certain cases to find strong expanders in an arbitrary graph. So you'll not be able to find the log n expander in an arbitrary graph, which keeps the same kind of size density as the graph has. So what they introduced is, okay, you cannot do that, but what you can do is precisely what your question was getting at. You can find much weaker expanders in any graph. So let me do a definition. An expander is sublinear. If lambda is tending to 0, so you should think of lambda, say, as being 1 over log squared, and everything that I'm going to say will be true for that choice of lambda. And the key property is that any graph contains a sublinear expander of about the same density. So you can run this paradigm of pass to an expander, use it to find your structure, but what you need to do is you can only work with these sublinear expanders. You will not be able to get the full power that might want. And the main problem with sublinear expanders is that they lose this robustness properties that I mentioned. So you will not be, in some sense, robustly well connected as you were here. Because imagine where we're working with 1 over log squared. So imagine that you have a set of size log squared. And sublinear expansion 1 over log squared only guarantees you one vertex connected to it, and it can be connected by a single edge. You remove that edge, you're disconnected. The network, you got nothing from your network. And these kind of issues are really problematic with sublinear expanders. But even despite that, they were extremely useful. There is now quite a list of conjectures and results that were proven and solved using these sublinear expanders over the last 10, 15 years. Perhaps the thing to highlight is a resolution of a 40-year-old conjecture of Erdos on odd cycle lengths, which was done by Liu and Montgomery. So this paradigm has actually been quite useful, even just working with sublinear expanders.
When you sit on tens, you want to have all the vertices?
I want it as a subgraph. So I want to find in my graph some subset of vertices, and then you would want to have as many, you keep all the edges, because more edges help you to expand. The more edges you have, you expand. So this it's induced, so if you want, but yeah.
I'm sorry.
Yeah.
But then, like, if I just take two vertices and an edge connecting them, like, I think I'm missing something. If you just want to find a sublinear expander, you can find one which is super small.
So two vertices and so yeah, I mean, for sublinear expanders, I agree. You want to keep the same density, and you probably want to keep something else. But yeah, so for two vertex thing, you are right. But yeah, it needs to be a bit big. And when you're working with just sublinear expanders, you also need to ensure something like minimum degree things. And so somehow, in order for it to be useful, you need to keep something more than density. Density will be okay for robust sublinear expanders. But again, you are correct. I should probably be more careful. I mean, the idea was just to kind of give you a flavor of where all of this was coming from, not so much to go into details. But good, so now finally I get to the robust sublinear expanders. And this is, so the idea is, again, due to Komlosh and Semeredi, they had two papers coming one after another. So the idea is this kind of pictures are very bad for you. You don't get robustness conditions for free from sublinear expanders. But what you can get is you can, in addition, ensure robustness on top of these sublinear expanders. So let me modify this definition on the top board into a definition of robust sublinear expanders. So now this becomes something explicit, and I'll just plug in specific numbers. And I'll change lambda expander. So a graph is said to be a robust sublinear expander if whenever you take a subset, which is again not too small and not empty and not too large, then either you get what we had before, just with an excellent, really, really good expansion condition. So in this case, you're really expanding very well, or you get that you maybe don't expand at all well, you just expand sublinearly, but you do it in a certain very robust way. So the robust neighborhood of U has size at least size of U over log squared. And what I mean by robust neighborhood is set of all V, so all vertices which have at least D neighbors inside of U. And you should think of D as being something like log to the 4n. Okay, so again, pictures are better than words, I think, at least for this kind of thing. So in the first case, what you get from your set U is that it expands really extremely well, but you only have maybe one edge from every vertex going there connecting to the set, which is first case. In the second case, you have your set, which expands kind of tiny amount. But what you have is that every vertex, or almost every vertex here, sends many, many edges going back, not just one. So in some sense, it's again hard to disconnect, because in order to remove a lot, you need to remove all of these edges to disconnect this piece from your graph. And this definition is ours. So this is with Richard Montgomery. And there are several competing ones, which have also found several applications over the years. And in particular, I like this one because it gives you the robustness from the definition of expansion rather than a separate condition. And it also led us to proving several very useful properties of these robust sublinear expanders, which are generally easy or much easier to do in normal, really good expanders. But you can get them in these things, which you can find in any graph, and then you can use them. You can actually even decompose any graph and almost decompose into this kind of thing.
Sorry, so constant valency graphs are never
So this is a specific choice of parameters which we worked with. You can adjust them and still get some kind of statement like that, but we are generally going to need to pay some kind of polylog factors if you want to find it in any graph. So you can develop the theory of this, but with this idea of how we want to use this, we already need to start paying some polylog factors there. And you'll not do better than this 1 over log squared n. And in general, the main idea, driving force, why we developed these things and worked with them is because we wanted to attack an old conjecture in combinatorics called the Erdős-Galay conjecture, which says that if you take any n-vertex graph, you can decompose it into just linearly many cycles and edges. This is about 60 years old. It's really central. People looked at it a lot. There are a lot of results, partial results, classes of graphs for which it's known, related problems for which we know the answer. And what we managed to do using this machinery that we developed is to get very, very close to it. So prove it up to a log star n factor. So log star is iterated logarithm fact. So this is this incredibly slowly growing function. So this is joint work with Richard Montgomery. And in some sense, it seems not so clear where these two things connect. So let me use the opportunity to shamelessly advertise that I'm giving a much longer version of this talk next week, where I'll hopefully be able to explain a bit better how all of this ties into this kind of problem and how this can be useful. Thank you very much for your attention.
Are there any questions?
Is it still true that you can find a robust sublinear expander in fundamentally any graph?
Yes, so with these parameters, yes, you can even decompose any graph if you're willing to sacrifice n times polylog and many edges. So we can decompose into just normal sublinear expanders by paying nothing, but if you want robustness conditions, then you need to start paying edges. I mean, need is a strong word. The thing is, many of the things that we're proving might be true in sublinear expanders. And if you can do that, then you prove that conjecture pretty much immediately. So the problem is that these things are super hard with normal sublinear expanders. And this gives you a lot of power and almost brings you back to the normal, like big expanders. Because in terms of edges, they're actually expanding well. But you can find them in any graph is really and even decompose graphs into them. Thank you.
Are those pictures dual to each other, the two pictures you drew in some sense, or?
So they're the two outcomes you might see for a subset. So you cannot exclude either of them and both will happen in a certain way. So actually this picture appears inside of this one if you look a bit closely. But so somehow if you take a random subset of this one, you will find some small set which expands really well inside of you. It's actually a very good, I mean, that's useful in certain things that we're doing, that somehow everywhere you're actually seeing this super good expansion picture. Just not that you can say that it's true everywhere for every subset. But yeah, so they're not dual, but they are very, very much related. There are two different cases which you might be seeing in your graph. Thank you.
All right, thanks for joining us.